Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a topic in physics, and this pertains to the concept of electromagnetic waves. In actual sense, under the electromagnetic waves, we are going to look at electromagnetic radiation, which is going to give us some of the clues on how we're going to handle some of the questions like the one that we have put on the board. So in this case, we're going just to have maybe a recap of some of the concepts that we have learned in some of our videos insofar as electromagnetic waves are concerned, and then we'll go ahead and try to tackle our question. So for that case, thank you and welcome. So as I've said, today we're going to look at a concept in electromagnetic waves. So sometimes we may come across this concept maybe being given as electromagnetic radiation, or maybe electromagnetic spectrum. And we're going to see in these different scenarios how these specific terms are being used, what is a radiation and maybe what is a wave, etc. So in this case, we're going to have a ways in which we're going to represent this. And in our case for today, which is a study of electromagnetic waves, we're going to look at the concept of electromagnetic radiation. Which basically will lead us to solving our sample question that we've got on the board, which says most of the light from a sodium vapor lamp has a wavelength which is lambda of 589 nanometers. What is the frequency of this radiation? So for us, in order to solve this kind of a question, we need to know some of the characteristics of these electromagnetic radiations and how we can be able to describe different forms of electromagnetic radiation. Now from this, it will be essential for us to understand what the concept of electromagnetic radiation refers to. And this comes from the concept of the word electrical and magnetic. So basically this is a compound word that is formed from the joining of the term electrical, but the concept from electrical and magnetic, which in actual sense refers to a form of energy that appears in forms of fields, which we are going to describe using an illustration. So basically this is a combination of electrical and magnetic fields, which of course are oscillating and causing disturbances. So when we were trying to discuss about the concept of waves, we said that a wave is a disturbance. It's a disturbance that is being propagated through space or maybe through a medium. So in this case, we are going to see also that the electrical and magnetic field can generate waves, and these waves are what we call electromagnetic waves. So in this case, we are going to look at the two aspects for electrical and magnetic fields, which are going to form electromagnetic waves. So therefore, when we talk about the concept of an electric field, when we talk about an electric field, we refer to a region around an electrically charged object. So therefore, suppose I have two charges at those specific points for the positive and negative charges, and assuming that those are the charges on an electrically charged object, therefore we'll have a region in space that is consisting of those specific lines of forces, which are going to indicate what we have called electric field. So these charges are going to move from the positive to the negative, just as illustrated by those lines. So therefore this is going to form what we call an electric field. Now that we have defined two concepts for electric and magnetic field, which are forming this compound concept or compound term that we are calling electromagnetic, We're also going to illustrate the concept of magnetic field and try to see how the two combine in order to form what we call electromagnetic radiation or electromagnetic waves. So in this case, we are also going to see that the magnetic fields, the field lines are running from the north to the south pole of this specific magnet, and they are indicated as such. So the interaction between electric and magnetic fields which we have termed as a form of oscillation or disturbance, is going to form what we call electromagnetic waves. So having illustrated this one, we're going to see that there's a way in which we're going to represent the electromagnetic waves. And from our study of the waves, in one of our short videos, we said that a wave has got this specific anatomy. And now we have longitudinal waves and transverse waves. Now for transverse waves, they have got a specific kind of an anatomy, in the sense that if they are oscillating in this plane, let's say this is the x, this is the yx plane, which we can be able to demonstrate using this one. Suppose this is a plane that is running along the y and x. Therefore, this region, flat surface that the wave is running along is what we call a plane. Now, suppose this is a wave that is running in this plane, and this is a electric form of electric disturbance, then we are going to have an electric field that is being illustrated as such. And then suppose we have another plane that is running along that line, and we illustrate that plane using this specific now this is another plane that is perpendicular to the first one. So therefore, if we have another wave that is running in this plane and it is perpendicular to the first plane, so therefore this will form the magnetic field in this particular space. So therefore we're going to see that the interaction between an electric and magnetic fields is what is going to form the electromagnetic waves. Therefore, the concept of electromagnetic radiation stems from there, and we have a wider range of electromagnetic waves, of course, or maybe radiation, which we're going to illustrate using the electromagnetic, what we call the electromagnetic spectrum, which is a range of frequencies, of course, for these electromagnetic waves that have specific characteristics, which we are going to see maybe generally how we can be able to illustrate them. So therefore, as I've demonstrated the concept of electromagnetic waves, we're going to see that electromagnetic waves come in different forms, and they form together what we call an electromagnetic spectrum, which I'm going to illustrate. Now this line forms a range of what we call electromagnetic spectrum, which is a range of energies that run from high intensity energies to low intensity energies, whereby this one can be demonstrated using the characteristic wavelength, which can be indicated from that. When we were trying to talk about the concept of a wave anatomy, we said that a transverse wave has got different parts, and we said that the distance between a crest to a crest or a trough, you can just continue this. This is more space. illustrate still using this. Okay, there's a traveling wave of this nature. The distance between a crest and a crest is what we call a wavelength. So therefore, the same case implies to the distance between a trough and a trough. We refer to this one as a wavelength. Now, this range of electromagnetic spectra forms wavelengths of different size, or maybe they have different intensity, from the high energy to the low energy. The separation of lambdas, as we can see from this one. Gamma rays have a very short wavelength as compared to the radio waves, as we can see. So in this case, we're also going to have to see that they come with the different characteristics. But there's some of the characteristics they share now that we have referred them to as waves, like the speed, etc. And we're going to see some of the characteristics which are being shared when we talk about the electromagnetic spectrum. So in this case, of course, the two concepts that we have learned, we're going to see that they are going also to bear significance in our sample question. And this is going to lead us to interpret some of the ways in which we can be able to answer these specific questions on electromagnetic spectrum if we are given in different forms. So we can go to our question and try to see what we were trying to solve, having been given a recap. So most of the light from a sodium vapor lamp has lambda. Lambda refers to the wavelength of 589 nanometers. What is the frequency of the radiation? Now, this conversion, of course, we're going to give it in the SI units. For length, the SI unit is in meters. So therefore, the conversion for this one is 589 times 10 negative 9 meters. Now that 1 nanometer is equivalent to 10 negative 9 meters. So therefore, I've done that conversion for that. And then what is the frequency? So I said there's a relationship between the wavelength and the frequency, whereby the wavelength is the distance between two successive crests or troughs, whereas the frequency is the number of oscillations or cycles per second. So sometimes this frequency can be given in form of f. So this initial can be used to designate frequency. So it's either an f or this form of designation that we have used for that. So there's a relationship between wavelength and the frequency for these electromagnetic waves that we have talked about, in that the frequency is inversely proportional to the wavelength. So therefore, this equation can be, or this expression can be written in the form of frequency equals c over lambda, where c represents the speed of light. Now this speed of light is a constant, which is 2.998 times 10. This is 8 meters per second. So therefore, we're going to use that constant. Now that we have been asked to find the frequency, we're going to use this equation to tackle our problem. So this is the case that is going to be applied for most of the ranges of the waves that we have shown in the electromagnetic spectrum, and other waves that we're going to encounter maybe in some of our studies. However, there's a different kind of waves that we're going to call the matter waves that stem from the concept of quantum mechanics, which we're going to see that they have a different treatment in that case. But for now, we're going to use this kind of an equation. And now that I've given that c is the speed of light for a constant, and the wavelength that we have been given, I've done a conversion for it in terms of the standard units. We're just going to do a substitution for our case here in order to find the frequency which we are being asked of. So the frequency will be the speed of light, 998.108 meters per second, divided by the wavelength is 589 times 10 negative 9 meters. So normally these frequencies are oscillations or maybe cycles per second. So therefore it's going to be given as per second or the units. So it is per second or hertz. Hertz, which is given as Hz. So therefore we're going to find the answer here in form of hertz, which is going to be, we can do a calculation to do confirmation of that. And in case we find that there's a variation, maybe we can have that one for discussion in the comment section. So I have this particular figure to just relate to two significant figures for a standard form, and then 10 negative 14 hertz. So therefore, given that we've learned the characteristics of waves from the electromagnetic spectrum, it's a general formula that we're going to use to calculate frequency or maybe the wavelength for that range of electromagnetic spectrum. And then we can be able to use the information that you have been given from the sample question in order to calculate either of these two concepts that we have been asked to. So we're going to just have a stop there, but it's important for us to know why we always study these basic types of questions, or the importance or relevance for us to try and study that concept. Now in this case, of course, I've mentioned about the concept of electromagnetic waves, and we're going to see that they have a wide range of use in our present day-to-day lives, in a sense that this electromagnetic spectrum, which I've listed, of course, from radio waves to gamma rays, are very important for us, in that the radio waves are used for radio and telecommunication that we use in our day-to-day lives. And then we had the microwaves, which were following the radio waves from the left side. I mean, they were on the right side of the radio waves. So in this case, these ones can be used for satellite communication, and even in cooking. We have a microwave ovens in our homes. So in this case, we are also going to see that there was an infrared range of this electromagnetic spectrum, which of course are applied in electrical heaters and even infrared cameras that are being applied for maybe night vision and etc. And for the visible light that we normally are conversant with, this is used in fiber optics, and even in communication, fiber optics communication. And for the X-rays, most of our medical procedures, and maybe some of our medical procedures, employ the concept of X-rays in medical imaging and treatment. And then lastly, we can have the concept of the gamma rays. Now these rays are used to sterilize equipment in hospitals, so it sterilizes medical equipment, and also even used in medical tracers, and then for radiotherapy for cancer patients. So in this case, I hope that we have tried to exploit part of the concept that is being requested of us in that. But I felt that this approach was trying to look at that concept in form of a summary before we tackle the question is going to open up other areas that we can be able to expound and understand the deeper concept, so that in any case we come across different questions that have been asked from a different approach, we can be in a position to solve that. So in that case, we're going to stop there for today. I hope that we have understood how we can be able to find the frequency, given that we've been given the wavelength and other areas using that general formula for the frequencies equals C over lambda. So that is it for today, guys. Bye. God bless.